Welcome to the second part of the video. Basically, we didn't need the second part. I was too tired at the end of the first part, so I left out a few exercises. Now, we completed till 6.6 of number 3. Now, number 4 is a bit complicated and I don't understand it quite well, so I'll skip number 4. Number 5 of 6.6 from the exercise 6.6. I'll do number 5 right now. We're recording it. So the question states that H is a hypothesis class of monotone Boolean conjunctions over 0 and 1. Monotonicity means the conjunction do not contain negations. So what they meant was that you can have conjunctions x1 x2. You can choose x1 and x2. You can choose only x1 or only x2. You can ignore a variable, but you cannot use negations. Like, this won't be a hypothesis for this example, so you only have two choices. Wait. You can so for your hypothesis, say you have three variables, x1, x2 and x3. Now for each variable you have two options. You can either choose or not choose. So choose or not choose, choose or not choose. So how many options do you have in total? You have 2 to the power the number of variables you have. Say you have the number of variables is d, so you have 2 to the power d options. So our question is the empty conjunction is interpreted as all positive hypothesis. So the empty one means all positive hypothesis. We augment HCOM with the all negative hypothesis. And basically I think they're referring that we don't need the all negative hypothesis here. So so I don't think we need +1 over here, but +1 +1 is so insignificant, you can always ignore the +1. Now if you consider having different so you have d variables, right? You have d variables in each of the wait so you have d variables, and with those d variables, say d is 3, so these are the 3 variables you have, and you can assign the values ignore or positive for ignore or true for these 3 variables. So how many so by assigning values you can classify 3 points if d equal to 3, but you cannot classify 4 points, and with with this reasoning you can just write that the VC dimension is D and not is greater than D or equal to D and is smaller than D plus 1, so the VC dimension is D. This is one way you can solve the problem. Another way is you can use the formula which takes into account the size of the hypothesis class. So the VC dimension of the hypothesis class would be smaller than log of the size of the hypothesis class, and here the size of the hypothesis class is 2 to the power D. We ignore the plus 1, so that will give us D log 2 and log and we can just ignore the log 2, so equal to D. But I think I prefer this one as it's more easier and will take much less time. So now for the next question, 6.7. the question states, we have shown for a finite hypothesis class H, VC dimension is smaller or equal log atom. However, this is just an upper bound. The VC dimension of a class can be much lower than that. Find an example of a hypothesis class of over the real interval x0 and 1 such that H is infinite while VC dimension is 1. So we have to find an example where the size of the hypothesis class is infinite but the VC dimension is 1. So the only function which has a VC dimension 1 we know of is the threshold function, and the threshold function is the function where before a certain value, so let us first draw the x and y axis. At the y axis, undo, x axis, y axis. Now the threshold function works in a way, say after reaching a certain point the value of the function becomes 1. So for value of x here it's 0, for value of x here y is 0, for value of x here y is 0, for value of x here y is 0, and after x reaches this point, for value of x y is 1. So at this point for value of x, for value of x here y is 1, for value of x, so the 1 at a 0. Now this has a VC dimension of 1 as we seen in the earlier video, but we have to show that H is infinite, so the size of the hypothesis class is infinite. How can we show that? It's really easy. Say you have this point, right? After reaching this point the value becomes 1, and before this point the value 0. So this point can be this point can be here. So this is a hypothesis 1. This point can be here, so this is another hypothesis. This point can be here, so this is another hypothesis, and you can have unlimited hypothesis in this hypothesis class. So size of this hypothesis class can be set to infinity. So that's how we can say that this threshold function with a in between a real two acha. Also, if we set a value like this must be between -5 and 5 for all real numbers, still the size of the hypothesis class is infinite. Why? Because I said real number. So in between, even if I said in between 0 and 1 and where they are real numbers, what is the size of the what is the size of the hypothesis class? So I can choose only values between 0 and 1. It's still infinite because you have 0.01, you can take 0.001, 0.00001. So in between a range of real numbers, the size of the hypothesis class is also infinite. But if I say in between 2 and 3, 2 and 5, where 2 and 5 are integers, if I say integers, then the size of the hypothesis class is not infinite, because you only have a few options. You have 2 and 3 and 4 and 5. So pay close attention to the question. If for real numbers an interval would be infinite, but for integers the interval is finite. Now for the next question, you have to show for the next example, you have to show for a finite hypothesis class over the VC dimension of a hypothesis class is log 2 base of h. So log 2 base of 2 is 1. Acha. So we can give any example we want here. So if we want to give an example of a threshold function, we know that the VC dimension of a threshold function is 1, and log 2 base of so somehow we have to make log 2 base of h equals 1. So 1 text, so log 2 base of h equal 1. So acha, on the next line we can write 2 to the power 1 equals h बाजे जगह लिख so this is the this 2 comes here, this h goes here. That's the formula of log to exponential. If you so the size of h will be 2. So how can we have a hypothesis class with size of 2. We can have a hypothesis class with size of 2 if we just define two hypotheses where the first hypothesis has the value of 0.1 here, so we define a hypothesis 0.1 here, and we can have another hypothesis where h2, where the point where the value, the changing point is 5, so we can have the second hypothesis where h is 5. So by giving this example a threshold function with two hypotheses, the second question can be answered. We can also use a different we can also use other functions to answer this question, like say we want that was the answer. Also you can write a different answer as well. Say you want to use the interval function. So what the interval function had a VC dimension of 2. So as we seen in the first video, so how much size do we need? So log 2 base of h equal 2, as the VC dimension here is 2. Now the size we need would be, we need 2 to the power 2 equals the hypothesis. So we need four intervals. So we can just define a hypothesis class which has 4 hypotheses, and you just can write h1, h2, h3, h4, where it contains interval it's interval functions, and it contains 4 interval functions, so this can also be an answer. So that covers chapter 6, exercises of chapter 6.